Okay, hello everyone. I'm Alam Segres. Today I'm going to present you our ICCV work called Deep Constraint Dominant Set for Person Re-Identification, which is a joint work with Marcelo Hilo and Mubarak Shah. Let me start with defining the problem of identification. You are given a query image. The task here is to retrieve all the person image which have the same person identity of the query image. Where the query and the gallery images are captured by a network of camera with or without overlap of field of view of field. As you can see here, the one with the green box shows the person image with the same identity of the query image, whereas the one with the red box shows the person image with a different person ID of the query image. So person re-identification is a challenging computer vision problems. There have been some works which try to tackle this problem by proposing different deep models. Here we can see some of them. Now I will give you a brief overview of each of this method. The first one is person classification network. In this case, this network casts person re-identification problem into person classification network. The second one is verification network. This is actually, this is basically a Siamese network with two heads or two outputs, which are the similarity score and dissimilarity score. So you are given a pair of image. The objective here is to maximize the similarity and minimize the dissimilarity if the pair of images are of the same person ID. Or if the pair of images are of different person ID, you maximize the dissimilarity and minimize the similarity. The third one is triplet loss-based network. In this case, we have three entities involved in the loss computation, which are the anchor, the positive image, and the negative image. And the objective of this network is to maximize the similarity between the positive and the query image while maximizing the distance between or the dissimilarity between the query and the negative image. Here we have the quadruplet loss-based network. In this case, this is similar with the triplet loss-based network, but we have 4 participants in the loss computation, which are the query image, the positive image, and 2 negative images. Similarly, with the triplet-based loss network, here also the objective is to maximize the similarity between the query and the positive image while maximizing the distance between the query and the negative image. The other one, and the one which is similar with our proposed network, is the diffusion-based network. In this case, there have been like recent works which try to integrate the classical graph-based similarity diffusion method into a deep neural network or in between the learning to exploit the contextual information hidden in the relation between given set of images. One example of such methods is a deep model which exploits a random walk method. In this case, instead of using like 2 image or 3 image or 4 image as in the previous methods, we're going to consider the entire person image to compute the relative weight. To do so, we first build the graph and then apply random walk method to find the random walk probability of each person image, and we do the optimization process in between the learning until we find the perfect random walk probability of each person image. By doing so, this method able to exploit or leverage the contextual information between the gallery image and provide context-sensitive similarity. But however, the problem of this method is they do not apply the diffusion process by considering the query image as the main point of the similarity diffusion, or the similarity diffusion is not query specific. Because of this, the learning process is not effective enough. To tackle this, we proposed constraint clustering based network. In this case, we optimize constraint clustering in between the manner. where the constraint here is the query image, and the positive image to the query image are considered as the member of the constraint cluster. Here is how it works, the proposed work. You are given a query image or a constraint and a gallery image. You applied a constraint clustering, or in our case, we applied a constraint clustering called constraint dominant set. To do so, we first build the graph based on the initial similarity, and we find a constraint cluster like this, where member of this constraint cluster are the positive image to the query, and the query here is treated as a constraint. And the outlier of this constraint cluster are the negative image to the query image. Here is the workflow of our proposed method. As you can see here, we have two branches. The upper one is the branch which involves the constraint dominant set, and the lower one involves the verification network. To see like the workflow of our method step by step, we are first given a query image and a gallery image. We first compute the ResNet 1.1 feature right before the global average pooling layer, and then we compute the difference of the probe image and the gallery, each of the gallery image, by applying element-wise subtraction, which is followed by a global average pooling and element-wise square. And then we applied a Bash normalization, which is followed by a fully connected layer to find dissimilarity and similarity score between the query image and the gallery image. We finally collect this similarity and dissimilarity score to find the similarity vector and the similarity vector and dissimilarity vector, where the similarity vector contains the similarity between the probe image or the query image and the gallery image, and the dissimilarity vector contains the dissimilarity between the query image and the gallery image. At the same time, in the upper branch, we take the features and then we apply global average pooling, which is followed by a dot product to find the similarity between the given set of images. And we applied a ReLU application to avoid a negative similarity. Once after we compute the affinity matrix by doing the previous operations, we fit the similarity matrix to the constraint dominant set clustering. And this constraint dominant set clustering gives us the membership score of each person image to that constraint cluster, which is the characteristic vector, or like the output of constraint dominant set. So we treat this characteristic vector or membership score of the constraint cluster as a similarity vector. And then we compute the similarity, we compute the dissimilarity vector by taking the additive inverse of the similarity vector. Once after we get, or we obtain the similarity and dissimilarity vectors from the upper and lower branch, we apply a similarity fusion by applying element-wise multiplication between these vectors using a fusion parameter called beta. And then after the fusion, we find the final similarity vector and dissimilarity vector, and then we applied a cross entropy loss. So far we have seen how we are using or how we are leveraging constraint dominant set in this framework. Now we are going to see a brief introduction of dominant set and constraint dominant set. Dominant set is a generalization of a maximal click into edge-weighted graph. Here is the formal definition of the dominant set. If you are given a subset of vertex S, which is a subset of vertex B, to call or to say this subset is a dominant set, it should satisfy these two criteria. The first one is internal homogeneity, and the second one is external inhomogeneity. When we say internal homogeneity, all the weights, all the members of the subset A's should have a positive weight, while all the vertices which are outside this subset A's should have a negative weight. Now we are going to see the intuition behind this weights. We're not going to see how to compute this weight due to time constraint, but we will see the intuition behind weights. Assume you're given this coherent set with 3 nodes, node 1, node 2, and node 3, with similarity of 20, 21, and 22. If we add a new node on the top of the existing nodes, which is highly similar with all the existing nodes, with similarity of like 40, 41, and 35. Since it's highly similar with all the existing nodes, we expect an increase in the overall similarity of the set 1, 2, 3, 4. So that if we compute the relative weight of this node 4 with respect to set 1, 2, 3, 4, since it's highly similar with all the existing nodes, we expect a positive weight. On the other hand, if we add a new node, node 5, on the existing node 1, 2, 3, 4, which is less similar to all the existing nodes, since it's not similar with all the nodes, we expect it's going to destroy the overall similarity of set 1, 2, 3, 4, 5. So we expect the relative weight of node 5 with respect to set 1, 2, 3, 4, 5 to be negative. So according to the previous requirements or criteria, node 1, 2, 3, 4 going to be a dominant set. But finding dominant set like this is impractical, especially when we are given like a large graph. So in 2007, Pavan and Pelilo established a one-to-one correspondence between solving this linearly constrained quadratic optimization and finding dominant set. Here is the one-to-one correspondence. If you are given a subset A, and if you compute its weighted characteristic vector using the formula here, this weighted characteristic vector should be a strict local solution of this linearly constrained quadratic optimization. The other way around, if you take the solution of this linearly constrained quadratic problem, support of the solution should correspond to the vertex of the dominant set. By doing so, we establish or we transform this combinatorial problem into linearly constrained quadratic optimization. The other variant of dominant set is constrained dominant set. In this case, the user specify a query or a constraint and force the clustering process to contain this constraint or query in the solution cluster. This can be achieved by simply modifying the previous linearly constrained optimization by subtracting alpha along the diagonal of matrix A, which corresponds to the vertex outside the query. Here we have this theoretical guarantee saying if we take alpha, which is greater than the maximum eigenvalue of the submatrix A, where this submatrix A contains the vertices outside the query, the local solution of this parameterized quadratic program will contain part or all of the constraint sets which are specified by the user. So this dominant set and constraint dominant set can easily solve it by using replicator dynamics, which is shown here. On the top of the proposed framework, to further enhance the performance of our model, we leverage a multi-scale ResNet 50 feature to fuse finally with the proposed network and get a better feature. Here is the auxiliary net. You are given an image. you fit this image to this network and find 3 different features from multiple layers, and you pass these features to 2 streams, upstream and the lower stream, and apply this set of operation. And after the real operation, we compute the triplet loss. And after the fully connected layer, we applied a cross entropy loss. And finally, we take the average of these 2 loss to find the final loss. And finally, at testing, you're given a probe image or a query image and gallery image. We first extracted the deep constraint dominant set feature and the auxiliary net feature. And we concatenate these features to find a single feature. And then we build the affinity matrix. And we fit this affinity matrix to the constraint dominant set. But when we apply constraint dominant set here, we proposed a new technique called constraint expansion. In this case, if you are given this probe image, and first you find the nearest neighbor to this probe image, and you apply constraint dominant set on this nearest neighbors, and find constraint dominant set. And from this members of the constraint dominant set, you take the one with the highest membership score of the cluster, and consider it as a constraint for the second one. The second one gonna use this both constraint, the old one and the new one, and we apply constraint dominant set on the entire gallery image. And we consider the solution of this constraint dominant set as our final rank. In the experiment, we have used 3 benchmark datasets, which are CHK03, Marquette dataset, and LookMTMC dataset. In addition to this dataset, we also aggregate a different dataset to train our model. For metrics, we use mean average precision and CMC curves. Here we have the ablation study. Here you can see the baseline result. When we say the baseline, it's like when we consider only the lower branch of our framework, which is the verification network. And HD denotes a single dataset setup, which means we train and test the model in a single dataset. And this one, MD setup, is when we train our model on multiple datasets and test our model on a single dataset. Here is the performance of our model. As you can see on a single dataset setup, as you can see here, we achieve a significant improvement over the baseline, which used single dataset setup. Here is the performance of our model in multi-dataset setup. Also here we have achieved a significant improvement over the baseline. Here in the last 2 rows, we have also leveraged the auxiliary net feature. We fused it with our proposed model feature. And as you can see here, using the auxiliary net give us some improvement over the method, our method without using the auxiliary net. Here is the performance of our model on CHK03 datasets. As you can see here, comparing to the state-of-the-art person identification method, our model achieved a sufficient improvement. Here we can see the performance of our model on market dataset. Also here our model achieved significant improvement. But here we also experimented by using a re-ranking method following the recent person identification method. So as you can see, in both cases, with using and without using re-ranking, our model perform better than state-of-the-art methods. The same here, we on Look datasets, our approach outperforms state-of-the-art methods on with using re-ranking and without using re-ranking method. Here we applied some parameter analysis. We evaluate the impact of fusing parameter beta on the performance of our model. As you can see here, the performance of our model perform well when we set beta to a larger value, which means our model perform better when we leverage, when we deviate much from the constraint dominant set branch, which is the upper branch. Here we assess the number of the number of image per ID during the training process. Also here, the performance of our model is consistent regardless of varying person image per ID in a given batch. Here we show the similarity score of the baseline method and the deep constraint dominant set method. The blue circle denotes the query image, and the green one shows the positive image to the query, and the red one shows the negative image. Here we set a threshold similarity score. As you can see here, there are some positive image which goes below the threshold, which means there are some positive image we are considered as a false negative. And so here there are some false negative, the same here. But when it comes to our model, it gives appropriate similarity for positive image, as you can see here, and the same for the negative image. Here we show some similarity heat map during the training process. This is the similarity heat map of the first epoch, where here we show the ground truth. Black one denotes the similarity between different person image, and the white one denotes similarity between same person image, which means 1 and 0. So here we show the similarity heat map at the 10th epoch and the 70th epoch. Here we show some qualitative results when we use only the verification network and the constraint dominant sets and branch, and we demonstrate the benefit of using this two branch. As you can see here, when we fuse them, we find a better similarity score. To summarize, for the very first time, we integrate a well-known theoretic clustering method called dominant set in the twin manner, and we optimize it in the twin fashion. And one-to-one correspondence between person re-identification and constraint clustering is established, and significantly improved the state-of-the-art performance. As a future work, we would like to investigate dominant sets clustering as a loss function. Thank you.